Alright, so this is an introduction to matrices, and I am not using the online system because I wanted to go ahead and create all the papers. There were some internet issues, so I'm just going to use this paper version and go show you how to work the problems. So a matrix can be used to solve systems of equations. And basically what you do is the last column is the number on the other side of the equal sign, and you usually write a bar. Every other column represents a variable. You could rearrange the order of the variables, but you just have to remember which one's which. So all of the x coefficients would go here, and y here, and z here. We normally do them in alphabetical order, but you could do them really in any order you want. But let me just take this over. And the way you would write the matrix for this is, so you put the line there, and that's kind of where the equal sign goes, and then you'll have x, y, and z. You don't write this. That's not part of the matrix. I'm just labeling it for you to understand. So the first one, you have negative 5x's and 5y's and negative 9z's, and it all equals 10. If you have one, if this was written out of order, so let's say that this was just written without this space, then the 6x would be over here under the y, so you just want to be careful and be sure and put that 6 under the x's there. 0y's, in that case, 3z's, and it equals negative 5. And in this one, we have no x's, 9y's, minus 7z's, and it equals minus 7. So that's how you write the augmented matrix. When you see row operations, it'll say multiply some number times some row. So this is row 1, and this is row 2. It might just say multiply row 1 by 5, or it can have sums and additions of different rows times different things added together. But that arrow means, and then put it in. Put it in row 2. So you've probably done before elimination on systems of linear equations. Basically, a matrix can be used to do elimination, but when you do this, you're using the same properties of systems of equations that you would use in elimination. So there is no goes to row 1, which means row 1 stays the same. So row 1 is still 1, 5, 2. But row 2, you take negative 4 times row 1 and add it to row 2. So negative 4 times 1 added to row 2. And then negative 4 times 5 added to negative 4. And then negative 4 times 2 added to negative 12. So you get 1, 5, 2, 4, minus 24, and that was negative 20. So that's how you do the row operations. Okay. All right. Row echelon form and reduced row echelon form are the two things that show up in your calculator. Oh, let me pull up my calculator. It opened before. Previously, these have been called Gaussian elimination and then Gauss-Jordan elimination. So basically, Gauss created a row reduction system to solve for systems of linear equations where the bottom corner was all zeros, and then Jordan came along and sort of fixed it up. So if you go to Matrix and go to Math, way down here below in the alpha section, you have REF, row echelon form, and RREF, reduced row echelon form. I do not know why anyone would ever do Gaussian elimination without Gauss-Jordan elimination. I have posed this to every class I've ever taught where we did matrices to let me know, should they ever discover a reason for doing this? No one ever has. So let me just show you the result of each. In Gaussian elimination, you have zeros in the corner here, but not anywhere else. But you have ones there. I'm just making stuff up, so it may be terrible. And the way you then read it off is, well, z is 6, because you have no x's and no y's in one z. That's 6. Then you use this here and say, well, y plus 2z is 4, so y plus 12 is 4. Y is therefore -8. And then you use both of these theoretically up here. I've got 0 z's, but x minus y is 3, x minus -8 is 3, x is -5. And then you get the result, -5, -8, 6. So this is row echelon form, where you have zeros down here and ones on the diagonal and anything else anywhere else. In this particular one, had we gone for reduced row echelon form, because I now know what the solution is, reduced row echelon form has ones on the diagonal, zeros everywhere else except for the constants. So reduced row echelon form would have looked like 1, 1, 1, 0, 0, 0, 0, 0, 0. Oops. Line -5, -8, 6. It would have looked like this. So kind of take this a minute. If I were to put this in the calculator, I would do it like this. Matrix. So remember that I went to matrix right here above x inverse matrix. And I would go to edit first because I want to input this matrix. So I'm going to put it in this row echelon form already. So I'm going to say, okay, I want A, and these dimensions are always row, column. Everything to do with the matrix, the labeling. If you say an element in a matrix A sub 1, 2, that means first row, second column. It's always row, column. So I have 3 rows and 4 columns. And 1, -1, 0, 3, 0, 1, 2, 4, 0, 0, 1, 6. And then quit. And then go to matrix again and go to math. Row echelon form I think is A. Oops. Well, you get to see this again because I did this crazy. Math, alpha, A, row echelon form. And then I go to matrix again, and just choose it. And it gives me back exactly what I had because it was already row echelon form. But then I can go, if it wasn't already, then it would give it to you here. Then I go back and I choose instead reduced row echelon form. So that's B. Still on this matrix. And this gets this one. -5, -8, 6, like that. So that's the difference between the two, and that's how you get them in the calculator. Okay, so this one just says, is it in row echelon form? The answer is no, it's not, because there's an 8 right there, and that should be a 0. Row echelon form has 0s under the diagonal and 1s along the diagonal. Okay, so this one, Gaussian elimination, again, is the row echelon form. Jordan perfected it sort of with the Gauss-Jordan elimination, which is reduced row echelon form. So I'm going to take that. The first thing I need to do is write this as an augmented matrix. And remember, it just had a number on one side and all of the like terms were collected. So first off, 4x plus 20y equals 6x plus y minus 46. And then that's rewriting the first line, but I really want these moved over. So 4x minus 6x is -2x. 20y minus y, 19y. Over here I have -46. This one, 15y plus 3x equals -18. So these are my rewritten lines. So that the numbers on one side, I need an augmented matrix. So I'll have -46 and -18 over here. Minus 2x's, 19y's. This is out of order. I have 3x's and I have 15y's. So I just write it in the correct order. Matrix, edit. This time I have 2 rows and 3 columns. -2, 19, 3, 15. Oh, -46, 3, -18, oh. I forgot to quit. So 4, -2 is the solution. X is 4, y is -2. In the case that you need to do this by hand for, wish this was smaller now. If you need to do this by hand for the final exam, feels unlikely, seems like a huge waste of time to put on a final, but because it's departmental, I can't be sure, so I'm just going to tell you, go through this like you would elimination. The first thing that we want to do, always, is get a 1 in the top corner. The next thing is to put a 0 below it, and then a 1 the next spot in the diagonal, which in this case there's only 2 spots in the diagonal. And then you would put zeros below that. So you always start 1 and then zeros all the way down, and then 1 and then zeros all the way down. But in this case it's just not that many, there's just 2. So the easiest thing to do, because we're looking at multiplying some row by something and adding it to some multiple of another row, and we're trying to get 1. 3 minus 2 already is 1. So the first thing I would do is row 2 plus row 1 and put it in row 1, and that'll get us that 1. So 3 plus minus 2 is 1. 15 plus 19 is 34. Negative 18 plus negative 46 is negative 64. And then I would also probably go ahead and divide these by 3 just because they all can be divided by 3. So I'd also do 1/3 row 2 goes to row 2. What you can't do is take some multiple of row 2 and put it in row 1. If you're going to enter it into row 1 had to be part of it. If you're going to put it in row 2 had to be part of it, or you lose the information contained in it. So I'm just going to change this to 1, 5, negative 6. Now I want a 0 here, so I can just do row 1 minus row 2 goes to row 2. So row 1 minus row 2 goes to row 2. So 1 minus 1, 34 minus 5, negative 64 minus negative 6. I need this to be a 1, so I'm just going to divide by 29. So at this point I have row echelon form. So I could just say, okay, well, now I know that y is negative 2, and so then I can solve for x on the top row there. To get, so this is Gaussian eliminated so far. To do Gauss-Jordan elimination, I now need to get a 0 up here. So the way to do that is to take row 1 and subtract 34 times row 2. So once you have this 1, you're always in a 0 to its left. And even if we were down here on this one, we would have zeros to the left everywhere, because that's the order in which you do this. Then we can multiply this by the opposite of that and add them up, and then it'll always give a 0 there. So row 1 minus 34 times row 2 goes to row 1. So row 2 stays the same. Row 1 minus 34 times 0 is still just 1, so that's the purpose of the 0 here. 34 minus 34 times 1 is 0. Negative 64 minus negative 2 times 34 is 68. So negative 64 minus a negative 68 is 4. Yeah, okay, so that's how we would get the answer by hand. So yes, it was much faster on the calculator, but okay, so 2 more here. Helen stayed in 3 different cities: Washington, Atlanta, and Dallas, for a total of 14 nights. She spent 3 times as many nights in Dallas as she did in Washington. The total cost for 14 nights was $19.80. And we've got the cost here, and we want to figure out the number of nights that she spent each day. If you have 3 variables, you must have 3 lines. If you have 4 variables, you must have 4 lines. If you have too few lines, then you can't solve. If you have infinitely many solutions. If you have too many equations, lines, then it's possible you'll have a contradiction. So we need to write down what we read here as linear equations. She stayed in 3 different cities for a total of 14 nights. So W plus A plus D is 14. She spent 3 times as many nights in Dallas as she did in Washington, so D is 3W. And then her total cost was $19.80. 210W plus 90A plus 130D is $19.80. So these are our 3 linear equations. This one we need to rewrite. So we could take this one and say 3W minus D is 0, for example. So now we need to write this as an augmented matrix. And again, normally we put them in alphabetical order, but because these are listed WAD every single time and I didn't name them XYZ, I'm going to have it just in this order here. So 1, 1, 1, that's 14. 3, 0, negative 1 is 0, so that's this line here. And then 210, 90, 130 is 1980. So 3 rows, 4 columns, All right, so she spent 3 nights in Washington, 2 nights in Atlanta, and 9 nights in Dallas. All right, last one. This is kind of fun, I think. So the systems of equations is when I plug in -2, then x squared is 4, so 4a, and then plug in -2 for x, so -2b plus c is 10.44. When I plug in 3, then x squared is 9, so 9a, x is 3, 3b. When I plug in 14, 14 squared is 196. Sorry, I had a little interruption there. There's a 1 there that we can't see, but we know it's there, so. Put it in the calculator. This is still a 3 by 4, so that's okay. Or -2 1, I don't know why I did that. I'm distracted now. Sorry. 9, 3, 1. 196. 14. Dang it. Enter. 14. 1. 148.36. And quit. So we have that A is 0.51, B is 2.5, and C is 13.4. So if we were writing this then as a quadratic, we would say, okay, then f of x equals 0.51 x squared plus 2.5x plus 13.4, and that is that.